Nothing will feel like it, especially using measure rank, it's like a common probe or like these things with what the Zell is open to journals.
Sorry. Okay, everybody, welcome. Thanks for showing up. It's my pleasure to introduce Joyce Huang, who is going to talk to us about estimating rainfall intensity duration frequency curve with duration dependent generalized extreme value distribution.
Okay, thanks for having me. My name is Joyce. This is my 5th year in Clemson. Today's talk is a in-progress work that's a joint work with my co-advisor, Dr. Brooke Russell and Dr. Jiyun Huang. The topic is about estimating rainfall intensity duration frequency curve with duration dependent generalized extreme value distribution. So in this talk, I'll briefly introduce an IDF curve, which is an intensity duration frequency curves. And to construct an IDF curve, one need to estimate the rainfall extreme events. To do so, we can model the rainfall extremes with a extreme value theory based distribution, which is a GEV distribution and its extension dGEV model. And later we will apply both model to a single model initial condition large ensemble to assess the extreme estimation performance. Well, as you can see, So as you can see, the heavy rain events cause damage to our life. And for one study, the rainfall events like me, I'm not a meteorologist. The only thing I know that impact the amount of rainfall precipitation probably is temperature or maybe the greenhouse concentration, right? So, but as a statisticians, we like to play with the data. So we can look at the rainfall precipitation data collections, and then we want to find a pattern and then use that pattern to make some predictions. So the first thing is for us as a statistician to study extreme rainfall events is to get the data and to see how those data distribute, right? So here's an example. This is a plot about the daily precipitation in Clemson from 1950 to 2010, and it's in yearly base, and those highlights blue points the maximum of that years. So in here, because not all the rainfall events are useful for us, right? Like today's rain, it may cause flood, may not, but the thing we focus on are those rainfall events that cause trouble for us. For example, it's a very extreme heavy rain events. So that must be kind of like a maximum for the per year. So as a statisticians, we want to know how those maximum rainfall events distributed. So the first thing, we collect all those maximum value. Then next thing, we make the histogram, and also we want to use a simple way to make predictions. So sometimes we will fit this curve to see how those frequency distributed. Okay, hope that makes sense. I'm sorry. The first time I play with this. So here is an example of IDF curves. This is d-GEV curve, is one type of IDF curves. the x-axis represent the duration and the y-axis represent the precipitation depth. And for IDF curves, the y-axis actually is the precipitation intensity is easy to transfer between two of them. And you may notice, first, the curve is continuous, right? And the second, the curve got different colors here, which tells us the information, how frequent such extreme events happen. So, and also here it shows you that different curves represent a different different reoccurrence interval year. To us, we call it a return period. So, when you can observe that as the return period increase, those lines also go top. So those are the two things I want you to keep in mind. IDF curve should continuous across duration. And the second is once those events with high return period, the line should go top. Okay. And why do we need IDF curves? IDF curves actually provide very valuable information for civil engineer or hydrologist to manage the risk of flooding or to build a ensemble dam or like a drainage system in the city. And also different durations we hear. Sorry about that. So in here, we want to involve the duration is because different duration may impact our life differently. Like for civil engineer, they may only focus on daily precipitation, but for the for those researchers studying for agriculture, maybe monthly extreme rainfall events is the thing they're looking for. So that's why we want also keep the duration into the study. So next we're gonna explain. We're gonna explore how to construct IDF curves. Here we can our goal is to estimate the ID of t for the given duration and the given return period. Accurately and efficiently. To do so, we can use this simple formula, right? All those d, t, that's a simple side are given. And so for the complicated rainfall events, one can use this elegant formula just to make a prediction. And here T is represent return period. ID of T is a T-year return level at duration D. We're using an example I3 of 10 here, which represents a 10 years return level of a rainfall intensity at 3-hour duration. The thing in the parentheses tell us the frequency of the 10-year return level. In here, this function actually is a inverse of the cumulative distribution function of rainfall accumulation over duration D, and the N of D is a sample size of duration. So our goal in here actually is actually estimate this function. Once we got this function, everything else is given, then we can calculate this step. So to estimate this this F, we can two popular way are quantile based method and the distribution based method. So quantile based model can be summarized in this general form, where AT is an increasing function as t increase, the whole A of t gonna increase. And to estimate A of t, it can be empirically, or it can be using some distribution model. And B of D here is a scaling function in terms of duration. One form could be like this, B here. So another way to estimate the F we mentioned before, the inverse function, is using distribution model-based method. And in our project, we typically consider the distribution of annual maximum and model it using a generalized extreme value distribution. I'm gonna introduce GEV later, very soon. So, as we saw this picture actually at the beginning, and here I just break it down in two parts. As I mentioned before, as a statisticians, we like the way we study something is to collect the data to see how those data distributed. And in here, I'm not sure how many of you know random variable well. The sample mean, sample maximum. So you guys all know why sample maximum is a random variable too. Hope so. So yeah, actually, just let me give you a short review on random variables. So random variables is a, for example, you want to collect the data of the rainfall precipitation, like today's per hour. It could be like any numbers from 0 to, I won't say infinity, but it could be, right? But it cannot be negative, right? So once you collect like for a month of precipitation per hours, so you got every day you got 24 hours, right? So that times 30 days, so that's your sample. So if you do that 12 months, you got 12 samples, every sample will have a maximum. They won't be the same, but they all belongs to that sample. So that sample maximum changes too when you sample change. So that's why sample maximum is a random variable too. So since it's a random variable, we want to know how it's distributed. So the first thing is, after we collect those sample maximum, in here, the sample size we are using is per year. Then we made a histogram. We first made a histogram of those sample maximum. And we also hope this histogram can be captured by certain curves, because we know we can use function to express those curves, which is more simple to do so. So before I go deep on this one, let me just talk extreme value theory. Let me talk something that you all familiar with, which is central limit theorem. Are you all familiar with central limit theorem? Basically, it's saying when your sample size is large enough goes to infinity, the standardized sample mean will have a normal distribution, right? Well, like central limit theorem, extreme value theory, kind of say for a random variable x with a IID distribution. Well, you don't need to be identical, but need to be independent. We let the m of n to be the sample maximum, and if we can find a n that's bigger than 0, bn belongs to the real number, and if we can standardize the sample maximum as the sample size goes to infinity, if this one converts to certain distribution, then that distribution must be the extreme value distribution of the random variable x. I'm not sure whether I can show the example in here. So how can I switch to the computer? Would that work? Okay. I'm not sure whether you can see that through Zoom. So here's some easy code to show you why we cannot use just the central limit theorem or just use the sample mean distribution to capture the sample mean. So in here, first I will sample some data. That work? Yeah. Then let me make a histogram so you can see it in here. Oh, I see what's happening. I need to copy it. Okay. Now you can see. So here's the histogram that I sampled from exponential distribution with the mean of 2. So then after that, after we got a histogram, we may want to see whether it can be captured by a curve. The change can be captured by a curve. So yeah, there's a certain curve can capture the change of the histogram. So let's do the whole thing for 1,000 times and also for each sample, we will calculate the sample mean and we will derive the sample maximum. And I will plot it. See, it's keep on sampling different different data. In here, the blue color shows you the sample mean, and the red red dot shows the sample maximum. So after it's done, it probably takes a couple within a minute to repeat. Let's keep on running. Then later, because we sample 1,000 times, we got 1,000 sample mean here. Oh, here it comes up. So then for those 1,000 sample mean, we can make a we can fit a distribution curve. That's the shape of the central mean, and here's the curve of sample maximum. It should be 1 plot. I don't know what's happening here. But as you can see, definitely they have different shape. So it doesn't make sense just use the sample mean to estimate the sample maximum, right? Also, it has different shape from the original distribution. The original distribution looks like this way, right? So since we're studying, since we are studying extreme rainfall events, we'd better choose some we'd better choose some reasonable distribution to model it, right? So in here, as we mentioned before, extreme value theory provides a theoretical foundation for us to model the distribution of extreme rainfall events. And the distribution can be expressed in this way. This is the CDF of that. And there are 3 actually based on the value of Kasi in here. Sorry, my bad, I forgot. The GEV has three parameters, which is mu tells us the location, sigma tells us the scale is a scale parameter, and Kasi in here is shift parameter. Kasi actually plays a very important role in GEV distribution. It tells us the value of the Kasi decide the tail behavior of the GEV distribution. So if the Kasi is bigger than 0, it's end up with a Fauché distribution, which means the up tail is quite heavy, which is a black one in here. If the Kasi is 0, which is a Gumbel distribution, it tells you the up tail decays exponentially. And if it's less than 0, it tells us actually the maximum events you study has a finite upper end in here, which can be seen in the green lines. So we also conduct a simple simulation to check that GEV do provide a better tail estimation. In here, the simulation setting is we sample the data from exponential distribution with mean of 8. The sample size for each sample, the sample size is that much, which means for every hour we take a data point, and we do that for the whole years. So that's the for whole years. Then for each year we derive the maximum, and we do that for 50 years. So each sample actually. Oh, I got it. So yeah, so the sample size in here is 50 years of the per hour estimation. And then we do that for 300 times. And with those data, we want to estimate the return period of 2 years and 50 years. To do so, the reason we like the exponential distribution is because we know the analytical form of the summation of exponential. Because in here, the data set, the data point represented per hour, we also want to estimate the return level with different duration. We can aggregate the data points from 1 to any duration we want. So if we sum any exponential random variables, the summation of the exponential will lead us to a gamma distribution. So in that way, we can use gamma distribution to derive the true return level. And after we apply 3 models in here, one is empirical method, another one is because the summation of the data points is gamma, so we think gamma may be a reasonable model to apply it with. So here we also use gamma distribution to make estimation. And also we use GEV too to see whether GEV is a reasonable distribution model. In this those 2 box plots shows the relative error of 2 years and 50 years. The way we calculate the relative error is we use the estimation of 2 years or 50 years minus the true return and divide by the true return. So as you can see, the 0 means you accurately estimate the return level. So in here, when the return period is small, like 2, empirical method actually works not bad. It works as well as GEV estimation. But when your return period goes up, that means the chance for such events getting smaller and smaller. So that will send those events should observed on the very uptail of the certain distribution. Then you will see empirical method tend to underestimate the rainfall events. So does gamma. GEV actually did much better job compared with the rest too. So then you may wonder, well, underestimate, what's the big deal? Well, actually it's pretty severe if your dam is not that high enough, because you're using the underestimation. So which first leads to very severe disaster. Second is you waste the money to building those infrastructure. So that's a valuable thing we can do. as a statisticians to include their estimation, include the estimation. Yeah,
At this point, do I get this right, that we're comparing our estimate to the data used to generate the estimate, right? We're not looking forward yet, we're just staying within what we used.
yeah, that's right. We're not looking forward yet.
Okay.
Well, actually, we can do that too, but in here, I just put 2 years and 50 years, just want to show, okay, when the return period is getting larger, dGEV got its own advantage. We can use that to estimate for 100 years, but as the return period getting longer, the estimation, because we only got 50 years data set, the estimation getting well, I won't say useless, but it's not that trustful. But in reality, especially in a meteorology study, to get a long time period data is pretty hard. Because as I recall, for the rain precipitation, we may get like probably 100 years records. And for those accuracy, it's hard to say. And it's not fine, I mean, it's not fine enough, which means they may only get a daily observation. They don't have, they may not have the hourly observation.
Just a few years ago, I downloaded a set that was supposed to be all observations for the entire world going back as far as they go. It was only 2 gigabytes.
Yeah, larger than that, yeah, larger than that, yeah. Okay, any other questions? If I could move on. I hope it's easy to understand. Oh, we did that. So so this slide mainly tells us GEV is a reasonable distribution model to study the rainfall extreme events. And again, previously we're talking about the distribution model. Then we got a model. How can we get the return level or the intensity or the amount of rain precipitation? The way to do so is to find the inverse of GEV, and which lists in here. So for the given duration and the return period, one can use those inverse function. We also call it quantile function to make the estimation. An example in here is the idea of 100 which you probably heard a lot. 100 years flood. Well, 100 years flood doesn't mean it happens every 100 years. It's just tells you the chance that flood should happen in the long run. You should be observed in per 100 years. It's a chance. It's not a reality. So the 100-year flood actually in statistical terms represent a 0.99 quantile. That's we want to looking after. So we can use this equation to calculate that. And here it tells us the quantile plots of different GEV distribution, as I mentioned before. The Kasi in here will lead us to different value of Kasi will lead us to different GEV distribution. Again, we want to estimate that accurately and efficiently. At first, at the beginning of my study, this one doesn't mean anything to me. But as further as I go, I realize this one is most important because you are not only focusing on one location. It's just even for South Carolina, we got a lot of cities, we got a data set. So efficiently, how to estimate the rainfall intensity efficiently is also a big issue because different data set will lead you to different, may give you different Kasi value, for example. So how to do that accurately is, efficiently is also important. Okay. And at the beginning, I mentioned you need to keep in mind that the IDF curves got 2 properties. One is continuous, Another one is once the return period getting larger, the line should go top, right? So if you collect the data for each individual durations, you can just fit the distribution GEV model. Each duration will give you different parameters, right? But it's supposed to be when the duration change, it's supposed to be changed smoothly, right? If you use different parameter to make the prediction for specific durations, it won't guarantee you will have a smooth line. So that's the reason we want to involve duration into the model, which allows us to construct this it should be smooth. Construct a smooth curve across durations. And also, as we mentioned before, for the real life data, we only probably have 100 years. So, if we have more data, the prediction gonna be more accurate. But that's not the case for studying the especially environmental events, right? So how to use data efficient is another concern. So by involving different durations, you actually allow us to pull the data by the nearby durations, which will bring more information for us to better or accurately estimate the model parameters. And also, if you apply the GEV model individually for each durations, you only can make inference on that specific duration. For example, 3 hours or 6 hours. So if I want to make a prediction for 4 hours, you cannot use either of those models, right? So that's another reason why we want to involve the duration into the whole modeling approach. So the possible dGEV model in here are those. So first, for this one, in our study, we call it 1C model. So it's in exponential form, but if you take log into both sides, it tells you it's a linear relationship on the log scale for the parameter and the duration. And so does the second one, but it tells us the slope of two parameters should be different. And the third one is the recently proposed model, because later we will show you that those two models inaccurately capture the change of parameters across durations. So we now apply this model to see whether it can better capture the change of parameter across durations. So dGEV models, to estimate the dGEV model parameter, we are using MLE. I hope that's familiar. You guys all familiar with that, and at least you guys know least square. Okay, simple linear regression. It can be either estimated by the least square method or maximum likelihood method. And then we're gonna show we're gonna apply those methods to a simple Monte Carlo experiment, which has the setting. We actually did that before, but previously we only used one data set, which has per hour, which only got a duration equal to an hour. And now in here, because we want to involve the duration, so we aggregate the data from 1 hour, 2 hours till 48 hours. Then we use the previous three model to make the estimation of return period of 10 years and 50 years. So here, let's check the assumption first, because previously we say if it's a functional form, it should be followed like this way, right? So let's check. In here, those black dots are the ground truths of parameter estimation, which derived from applying GEV to all the 300 times 50 data set together. Since the sample size large enough, we just assume that's a ground truth of the parameter estimation. So the study we are focused on is trying to capture those change of those black dots across the duration. And one thing I need to mention, for parameter mu and the sigma, both in log scale. But that's not the case for the shape parameter, because shape parameter, some of the shape parameter is less than 0. You cannot do log on that. So as you can see, the black one can capture the dots very well, and that black one actually fitted by the last model we proposed, the GAN model, and the blue line in here is the estimation by maximum likelihood with 1C model. The red line is estimated by the least square method, and the green line is estimated by the MLE method of 2C model. So in those three shows, the black line, which means the GAN model, can capture the change of parameter across duration better than others. In here, you didn't see the green and the blue line. Yeah, you didn't see the green and the blue line. It's because it's far away from 0. It should be like on the top, and the scale is in here is from it's till like probably 0.001, something like that. So that indicates MLE 1C and 2C model well, estimating the C parameter is not that useful. And the plot in here tells us well, it's a ratio of mu over d, because previously the model suggests they should have the same slope. So if you take the ratio of both parameters, they have the same slope. It should the ratio of them should be a constant. So when you plot it, it's supposed to be a line. But as you can see, it's not a horizontal line. So which means the first model actually doesn't make sense. The assumption doesn't hold. So then let's look at the performance. On the top plot in here is the GEV. It's fitting GEV to each individual durations. The way we didn't graph it in terms of line, because you apply it point-wise in terms of duration. So it's inadequate to just connect them as a line. So the rest of them are the different dGEV model. The one in here is the GAN model I think this sorry. It should be the 2 years. Yeah, 2 years return level. So those the black line in here are the true return level, which can be derived from the gamma distribution, as I listed before. All those dashed line actually derived by the functional box plot. It serves as a confidence 95% confidence interval to tell you that whether the model can capture the change capture the shape of the line. So as you can see, GAN model will capture the line, so it's above there a little bit. If we shouldn't increase the confidence interval, but at least it captured the trend of the line. But for MLE 1C model and least square 1C model, it only write in this durations. And all other place, it's all out of those boundaries. So we don't think both model inadequate to capture the functional form of the parameter versus duration. And that's the case to the MLE 2C model and the least square 2C model. So since it cannot capture well capture the line, so we want to see whether the model can improve, make improvements on certain durations estimation. Particularly, most of the civil engineers are focusing on the daily precipitation, which is 24 hours. So we then calculate the relative error of the return level for 24 hours. And the method is in here. For different, as you can see, there's no unique rule to say which model performs outperforms well than other method, because different return level shows different provide a different method in terms of the estimation. So, but overall, GAN model has a very, which is in the second in here, has a very small variability, which also very close to the true value. And in here, you can see as the return level increase, this square 2C model in terms of estimate the daily precipitation is much accurate compared with the rest of the method. So the dGEV model cannot capture the overall change, but it does improve the estimation for certain durations compared with GEV model. As you can see in here, GEV model is also underestimated, especially compared with the least square 2C model. And the GEV model tends to have large variance, which make your estimation unreliable. So at least through apply the dGEV model in the simulation data, we can see that dGEV model do have its do improve the estimation compared with just simply apply GEV model to each individual duration. So then later we apply the model to a more realistic simulation data, which is a CAN RCM4 data. Here we only use the first 50 years output. The reason we prefer this CAN RCM4 data, it first contains 35 member initial condition ensembles, and all of those ensembles are nearly statistically independent. And it covers the North American regions with the temporal resolution of 3 hours. And then later we can aggregate all those data set to till 48 hours. And in our project, we try to estimate the return period from 2 years to 100 years. This large data set is more close to the real life rainfall precipitation. As you can see, those blue lines are just the simulation simply generated from exponential distribution. On those red lines are the data set that derived from CAN RCM4. The very trivial thing is you can observe the zero. No, that means no precipitation, which is more realistic in the real life. But it's hard for exponential distribution to do so, because for a continuous distribution, the chance to be exactly a certain value is 0, right? I hope you guys don't overlook that. So because this data set is too big and this our project is still in progress, in here we only study for the data set from those yellow dots. Even though it's still very large data set. So just imagine for each point, we will have 35 ensembles. Each ensembles we will study for 16 different durations. So that's for each data point. Each point in here represents 16 times 35 data set. And if just select 10 points, that means about 16 times 35, you still need to times 10. So now you can see why efficiently estimate rainfall return level is important. In here, we're only talking about 10 points, but think about the whole United States. And to estimate those 10 points, even very time consuming. It takes like probably a day to calculate those data. So efficiency is important in here. You don't want to get some result, accurate result when the events already happened, right? So in here first, again, we want to check the model assumptions for more realistic data. So first, we generate we derive the ground truth parameter, which is estimated by fitting dGEV model to all 35 ensemble data together. The reason is more data. If we got more data, we will have more accurate estimation, right? So then we plot those parameters for each durations into the black dots. And in here, we try, it's hard for you to see different, like red, green, or blue. It's all covered to each other in here. But as you can see, they definitely now will capture the change of those black dots. Then it's for the scale parameter, it looks like it's reasonable to assume it's a log linear between the sigma and the duration. And for the shape shape parameter, which is the hardest one to estimate. So for the first two model, they assume the shape parameter to be constant, which in here is not the case. In our project so far, because the difficulty to estimate the shape parameter, in our project so far, we just assume that shape parameter to be constant across duration. So it's like this one. And again, we want to check whether the same slope is a reasonable assumption for mu and sigma. As you can see, it's definitely not a horizontal line. And we select more location to check for the assumption, and we observe that to be constant C should be problematic. And that's gonna be our future study to see how to model C in a reasonable way. Then we want to see the performance of those dGEV model in a more realistic data set. So here is the estimation of 2 years return level. As you can see that in here, the GAN model will capture the ground truth in here. But all the rest, those ground truths are not in those confidence interval cannot capture the whole line. So at least the new proposed model GAN does have some improvement in terms of estimate return level by involving the duration. But when we try to estimate the longer year return level, the case is not the same. There's no one method can totally cover that black lines. So, well, our study is still in progress, and this is just about one location and one ensemble. It could be because the ensemble is a little bit biased. But later we will see how to improve that. I think I'm gonna wrap up today's presentation. So today we discussed some commonly adopted dGEV models, such as like 1C model, 2C model, and the way to estimate it by MLE or by d square. And then we also proposed our own model, which is a GAN model. And dGEV model led us to estimate fewer parameters, and also can provide benefits for return level with a large return period. And also dGEV model, as I mentioned before, it allows us to estimate the return level smoothly across duration, which cannot be achieved simply by applying a GEV model to each individual duration. And for the further study, we want to consider the dependency across duration. Remember, we aggregate the hourly data or 3 hour data. So, which means the 6 hours data is dependent with 3 hours data. Okay, so how to model those dependency gonna be another concern to improve the estimation. Another thing we can think about is by applying the pooling strategy to with spatial factor like Clemson and Greenville are very close. We can borrow the information from Greenville to improve the estimation of Clemson area, right? Also, as we all know, we are currently under climate change condition. So, which means the estimate, if we still use model for stationary climate change, which will definitely underestimate the future rainfall precipitation, and that's useless. So how to make a model allow us to incorporate the non-station narrative is very important nowadays. So that's the presentation for today. If you got any questions, feel free to ask.
Any questions?
Have you done any back testing? Are you going to? And by that, I mean specifically, if you only have 50 years data, take the first 40, rederive everything, and give me statistics for the next 10 and see how it compares.
No, even like with 50 years data set, it still sometimes will provide unrealistic parameter estimation. So data, the lack of data is the big issue in event study. So we're not using that. And also the GEV model is the reason we're using GEV model is because it allows us to do to make a focus for the long period. Like even if we got 50 years, we still can use that to estimate 100 years return level. But if you use that to estimate like 1,000 year, it may not be reasonable. 100 years still good, I think.
Other questions? Let's thank our speaker. Stay tuned for next week. We'll have Wayne Goddard, who will be talking to us about something quite interesting, I'm sure. You kill it.